So a magnetic field is produced by a moving charge. So this was thermodynamics, and now we're going to get into electricity and magnetism, and then we'll combine the two of them together and actually see how this generator works inside of here. So the key thing here, just to remember, back to physics, the cross product. So velocity is a vector, the radius is a vector. We have to take the cross product. So right-hand rule, be able to apply that. And just kind of remember that if the arrow, because we're going to typically draw things in 2D, but then we have to have the 3D component, because even on 2D we do the right-hand rule. One of them comes into the page or out of the page. So you kind of draw the feathers if the arrow is going into the page, draw the point if it's coming out. Okay, so let's work on some problems. So we have a charge moving through free space. We can think about this charge moving through free space with this velocity going in this direction. We can think about it as a wire if it's a straight line. So let's just imagine that this charge is kind of moving along a wire with velocity v2, and this charge has charge q2. What is charge measured in? What units? Coulombs, great. So this charge has q2 coulombs, and we're observing up here. So this is where we want to say, what is the magnetic field here? So some distance away from the charge. So this is some, nice. So some distance r away from that charge, we want to say, what is the magnetic field right there? So the way that we would do that, remember that the magnetic field, so if a cross product produces a new vector, right? A dot product produces a scalar, a cross product produces a new vector. And we want to do V cross R gives us the direction of the magnetic field. So V cross R, magnetic field's going into the board, so I see X's from the arrows going the other way. Good with that?
One more time.
What's that?
Can you do it one more time?
So V cross R means that the arrow goes into the board. So do this on your page, because or the other way, shoot, what is it? Like this. I always forget this one. So thumb is A, index finger is B, then your middle finger points in the direction of B. So A, V cross R, your index finger goes, or your middle finger is then into the board. So now let's look down here and see what direction our charge. So now we have, now our distance R from our charge to our point of observation. So if you just want to write a little like squiggly note to say like that R is from the charge to where you are saying what is the magnetic field at that location. What is the magnetic field at the charge? So if R is 0, then the whole thing goes to 0. So, but we also have this actually, so it actually doesn't, because down here we have another R squared. So it still kind of increases. So this is the R vector. This is the absolute value of that vector squared. So as it doesn't go to 0, because it actually just goes to 1 over R, so it actually goes kind of to infinity right at the charge, because we have this other R out here. So as you go further away, it drops down at a rate of not 1 over R squared, it drops down at a rate of 1 over R. Essentially drops down, yeah, because the R's cancel out, so essentially the magnitude of those R's cancel out. Okay, so V R, we now have it coming out of the board, so we see the points here. So now let's think about, so what I essentially just showed you was, this was the top point, this was the bottom point. So at the top, so essentially if the page was, if the screen was like my palm, and the charge was moving from right to left, so essentially the first point we did was going into the board, right? And then the second point we did below the wire was coming, actually we could say this point up here. So this point was above the wire and it was going into the board, and this point was below the wire and the magnetic field was coming out of the board. Essentially, if you did that in 3 directions, you swept the board, you would essentially see that the magnetic field creates a circular magnetic field. And so we can actually take that equation that had that cross product in there, which was kind of annoying because we had to use our right hand rule, and essentially boil it down to this constant. Remember that this is just a universal constant. We just have to be careful of what units we use. Times I, the current. So essentially, current is the charge per area, essentially, of the wire. So essentially, the charge flux going through the wire. Divided by 2 pi r. So the further away we are from the wire, our magnetic field drops at a rate of 1 over r. And our magnetic field is proportional to our current. So if we double the current, we double the magnetic field. If we double how far we are away, we cut the magnetic field in half. Because it's 1 over r. We quadruple it, we cut it by 1/4. If we quadruple r, we cut the magnetic field by 1/4. And you could kind of imagine that if you put, we'll get to that point. So now let's kind of look at if we take that wire, and so we first looked at a charge moving in a straight line, and then realized that a charge moving in a straight line was like a wire. But now let's take that wire and bend it into kind of a coil. So in this case, this coil has 1 turn. We could imagine this coil kind of going around a couple times and then coming back, and we could have multiple turns to our coil. But let's just look at the wire right here. Let's go back. So one reason why I like doing the right hand rule with the palm instead of the 3 fingers is that if you do essentially, if you can also do the right hand rule where you essentially wrap your hand around the wire and then your thumb goes in the direction of current, and the magnetic field essentially just wraps around like your hands do. It's a little bit of a different right hand rule, but it applies essentially the same way. And we can see that here. So that if we put our thumb in the direction of the current and then we bend our fingers around the wire, that this circle that our bent fingers make essentially is the clockwise or counterclockwise direction of the magnetic field. But if we do this all the way around, we see that all of these right hand rules are creating magnetic field that comes out of the middle of the coil and then goes into the board all around the coil. And so what we essentially get is we get this kind of focus of magnetic field into this coil. And so what is the magnetic field at the center of this coil? You can ignore all the calculus here of the equations above. But if you really wanted to derive each of these equations along the way, this is how you would do it with the calculus. That we essentially have, this is for a single coil, we have mu, 1/2 mu naught, and essentially I over R. And then if we add more coils, what do we think happens here? Do you think, if we had 2 more coils, does that double it? Does that quadruple it? Does that half it? it doubles it. So essentially, we can just write IN here. So essentially, if we double the number of coils, we can double the magnetic field. Or if we double the current, we can double the magnetic field. If we cut the radius of this circle by half, then we can double the magnetic field. What would be a challenge about doubling, just continually increasing current?
Heat.
Where would the heat come from?
Current.
Why would the current generate heat?
Resistance.
Resistance of what?
The wire.
This wire. So this wire here is not like perfectly conductive. It has some resistance, and we'll find out this in a couple minutes. Some of you, perhaps the less intelligent of you, might end up with burnt wire in your hands. So you have that to look forward to in a couple minutes. So exciting, right? I told you we'd have some fun activities. Okay, so far what we've learned today is that if we have moving charge generates a magnetic field. Okay. Moving charge generates a magnetic field. Now next, so there's three main kind of sections we're learning today. One is, I'm pretty sure that's Ampere's law, right? Yeah, so a moving charge generates a magnetic field. That's Ampere's law. Next we have the Lorenz Force law, which is that a current generates a magnetic field, but if we take that current and put it in an external magnetic field, we essentially have an artificial magnetic field, an electric magnetic field, in another magnetic field. Those two magnetic fields are either going to repel or attract to each other, and so they're going to have some force. So a current in a magnetic field results in a force on those charges that are resulting, that essentially make up that current. So we can have this in essentially two notations. This is the free space notation, where we have a moving charge in an electric field E, so moving charge Q in an electric field E, moving with velocity vector V in a magnetic field B. So E, V, and B are all vectors. And remember that a charge in an electric field feels a force without it even moving. So if magnetic field, if B is 0, there's still a force on this charge due to the electric field. So if we put a charge in an electric field, it has an electric force on it. If we put a charge, let's say the electric force, the field is 0, and we have a velocity and a magnetic field. So if E is 0, then the magnetic force, so this is essentially the electric force component, this is the magnetic force component, or the electromagnetic force component. And this term is only non-zero if the charge is moving. So the current, the charge has to be, Q has to be moving in order to feel a force due to this external magnetic field. So it's kind of confusing in this notation, but this notation is actually the fundamental notation behind how cathode ray tube TVs work. Remember I said we're shooting electrons at a screen. How do we steer those electrons? We can steer those electrons with magnets, because those electrons are moving with a velocity v, and we can change the magnetic field. And that's why when you walked up to that old TV with a magnet, you would kind of mess up the screen temporarily, because you would essentially cause those electrons to skew as they're flying at the screen. But in this class more, we care about just a simple wire. So if we just have a simple wire, we can have a force on that wire. So if we have current flowing through a wire, so current L flowing through a wire of length L, current I flowing through a wire of length L in a magnetic field B, external magnetic field, then that wire feels a force F. Okay, so let's look at an example. So we're just going to take, so I took that, I said the electric field component, the external electric field component is 0. So we're just looking at a charge moving in just a magnetic field, no electric field, with velocity v across the magnetic field v. So let's look at this charge. So this charge is moving to the right, so a charge q, moving with velocity vector v. Which way is there going to be a force on this charge? Well, we have to know where the magnetic field is. So let's say the magnetic field is coming out of the board. So magnetic field is coming out of the board. So V cross B tells us the direction of the force. So first of all, what direction is the instantaneous force on this charge going to be? Up or down? Down, right? So we see the magnitude of this force, or the magnetic field is going to be, or magnetic force is going to be down. If this particle is just left in free space, so I shoot a particle in this magnetic field and it's just allowed to move around in a frictionless environment, so this force is going to cause it to move. What kind of path is this charge going to make? So what direction is that charge going to move? Down, right? Okay. So that charge is V cross B makes that charge move down. Okay, well let's say that charge starts diving a little bit. So V cross B now means the charge not moving down, it's kind of moving diagonal. So it's kind of it's being sucked at me more. Okay, so it's now coming down even more. V cross B, now it's coming this way. This charge is just going to go in a circle. And that's how we get to this. So essentially we have a charge, this is a free charge. So remember, if that charge is attached to a wire, it can't move when that force is applied unless that wire moves. It could just create a force on that wire. But if that charge is allowed to just move free, it's not attached to a wire, it's just floating. Essentially, like think about that, actually, think about electrostatic precipitators, right? So electrostatic precipitator puts a charge and essentially causes it uses the electric field component to suck it to the, or to attract it to the collecting panels, I guess. So essentially think about this as a positively charged dust particle in a magnetic field gets essentially, so in this case, it is V cross B going into the board, so the force is going this way. And so here we essentially see our cathode ray tube shooting out electrons with no magnetic field, or, not an animation? Oh, there we go. There we go. So as the cathode, so this is a cathode ray tube just shooting out electrons, and then we have a big coil this way that essentially we create an electromagnet with, that we can either force the magnetic field to go into or out of the board, which causes this electron beam to either be forced up or forced down. And that's how they're able to scan these electrons across the screen to create a picture. Pretty cool, right? Okay, so a force on a wire. So we have a charge moving with velocity v and a magnetic field going into the board means that there's going to be a force this way on the wire. So this whole wire is going to move, because like assuming that the wire is a rigid wire and it can't bend, it's just going to move. So this whole wire is going to have a force and it's going to want to move this way. Any questions so far? Okay, so now we know that a moving charge creates a magnetic field. A charge in a magnetic field creates experiences an electromagnetic force. So let's say we don't have any external magnetic field, but we have two charges. No external magnetic field, we have two charges. The first charge creates a magnetic field that the second charge is moving. Second charge also creates a magnetic field. And those magnetic fields that those other charges are creating affects the other charge. And so we can essentially get this interaction, we get this electromagnetic interaction between two charges floating through free space. Essentially they're interacting with a magnetic field that didn't exist except for the reason that we have those two charges moving. So that's why we always talk about E&M or electromagnetic forces or electromagnetic interactions. Because essentially if we have two moving charges, then they're interacting through the electric force. So essentially what I did was I took this B field here and I replaced this B field with the B field that was created by charge Q2 moving with velocity V2, a distance r from Q1. And then this second boils down into the Lorenz force. So we have and essentially the electromagnetic force on an object is the electric force QE plus the magnetic force Q quantity V cross R. And so charge Q in electric field E, the electric force on that charge is in the same direction as that electric field. The electric force is just a scalar multiplier of the electric field. The electric force is just a scalar multiplier of the electric field. That's the electric force component, this QE term. And then the magnetic field, so we have a charge Q moving with velocity V. And notice that we only have a magnetic field if we have a velocity. So we have a Q, V, so V cross B in this direction gives me my magnetic force going up. So F mag is Q times V cross R. So V cross B, I'm sorry, V cross B, not V cross R. V cross B gives me my magnetic field, so this term here. And then essentially I just add these two vectors together. Remember that when you add vectors together graphically, you can just kind of create the opposite side of the parallelogram, and then that gives you the point of those two forces. Any questions? Okay. So now we have these two charges. So we have Q1, and so Q1, and we're just calling Q here, and then Q2. So this is the electric field component. So this K, or this Q2, R2, R vector, essentially, this is the electric field produced by Q2. A charge produces its own electric field. Remember, what does the electric field look like from a charge? Does it radiate out, or is it concentric rings? It radiates out. The electric field radiates out. Essentially, it looks like a star. And so that's we essentially see that in this R vector term. Essentially, the further the electric field goes in the direction of R away from Q2. So this is the electric field caused by Q2, but Q2 is also moving, and so this is a magnetic field caused by Q2 that Q1 feels. So we have two different charges, and this charge is causing an electric force on this charge, but also a magnetic force. So the electric force, so let's say that they're both positive charges, the electric force is going to cause this Q2, if they're both positive, they're going to want to repel each other, right? We have the electric force repelling each other. And let's say that they're both moving in the same direction. They're both moving in the same direction, then the magnetic field produced by Q2 produces a magnetic field because it's a charge moving with a velocity. A charge moving causes a magnetic field. So what is the magnetic field essentially here? It is so the electric field that is the magnetic field at Q2 caused by Q1. So remember, we start at Q1, we bend towards where we want to look, and then our thumb points into the board. Down here, we look where we want to see our electric field, and down here we'll have the magnetic field coming out of the board. So it just kind of shows you how two different charges can cause kind of this electromagnetic interaction. Okay, so
So
Yep.
if you have two of the same, if they're both positive,
yep,
that means that the magnetic field are going to be opposite direction.
yep. And if I told you that these were moving electrons, everything just flips because you essentially just add a negative sign here, which means all your vectors flip around. Okay, so we said that a moving charge creates a magnetic field. A charge moving in a magnetic field experiences a force. And now the third one, Faraday's law. So Faraday's law says that a changing magnetic flux, what is a flux?
Change of time or the rate.
It is it's essentially the amount going through an area. So the magnetic flux is essentially how much magnetic field is going through an area. The magnetic flux is how much magnetic field is passing through an area. And what I'm saying is, if that number is changing, so if the amount of magnetic field passing through an area is changing, that induces a voltage around that area. And so there's three different ways that we can cause a change in magnetic flux through an area. The first one is we can just take a magnet and change the magnetic field. So the amount of magnetic flux, remember, is the amount of magnetic field passing through an area. So let's say that the area is the circle of the core of this coil of wire. So what we can do is, remember, as we move the magnet further away, the magnetic field drops off 1 over r. So the magnetic field drops off 1 over r, and so as we move this away, there's going to be a changing magnetic field. The magnetic field that this coil observes is going to be decreasing. And so if we move this coil kind of up, or move this magnet up and down, we would cause an alternating voltage. As it's moving away, the voltage would increase. As it's moving closer, the voltage would decrease. Or possibly the other way around, how you look at it. So there's three different ways we can create a changing magnetic flux. We can change the magnetic field. We can change the area. Or we can change the angle at which the magnetic field hits the area. So you can imagine that essentially, like, if I'll let you write those three things down. So three things are, how do we create a changing magnetic flux? We can change the magnetic field. We can change the area. Or we can change the angle at which the magnetic flux intersects the area. And that essentially boils down to this equation here, where the magnetic flux is equal to the magnetic field times the area times the cosine of the angle at which the magnetic field intersects the area. This is actually a nasty surface integral, but for everything we'll be doing, it's going to be a 2D area, so surface integral just simplifies down to that. And then the area of, assuming that the B field is constant across the area. So here, we're essentially changing the magnetic field to change the magnetic flux. So we're moving this coil up and down, and then that's causing this current meter to go back and forth. So as the magnet is coming into this, it's increasing the magnetic field here. As the magnet is going further away, it's decreasing the magnetic field in this area. Well, who says that this has to be a permanent magnet? Why can't this be an electromagnet? And so if I have an electromagnet, if this is just a battery, does the battery produce direct current or alternating current? Direct current. Batteries produce direct current. And so this is essentially the B field here is going to be constant. Remember, so this creates a direct current. A moving charge creates a magnetic field. So we have a magnetic field created from this electromagnet that is going into this area here. But because the magnetic field is not changing unless we move it up and down. So if we move it up and down, then we can induce a current, or we can open and close this circuit. So we can charge the magnet and we can discharge it. We can charge the magnet and we can discharge it. And then that changing magnetic field from this electromagnet is going to be observed by this coil and induce a coil. Any idea what we might call this? It's a transformer. So a transformer essentially takes electricity, takes alternating current electricity. Transformers only work for alternating current. So we take alternating current, feed it into one coil, create an alternating magnetic field that feeds into another coil where we generate a magnetic or an electric current again, or an electric voltage.
So what do they mean when you say that you blew a transport?
It means that you put so much current through these coils that you've heated them up so much that they've melted together and essentially short-circuited. And yeah. Okay, so a review of kind of the three different ways that we can create this changing magnetic flux that creates this proportional change in voltage. So here we see a changing magnetic field. The dots, the arrows going into the board are getting further apart, getting closer together, further apart, closer together. This alternating magnetic field creates an alternating voltage, an alternating current through this coil. The other way that we can do it is we can change the area inside of this loop. So we can essentially stretch the loop bigger and make the loop smaller. Stretch the loop bigger, make it smaller. So we're essentially changing this A term. So here, we're changing the B term. Here, we're changing the A term. And then the most exciting thing, we can change the angle at which the magnetic field intersects. So when the circle is like this, the maximum amount of magnetic field is passing through it. But when the circle is like this, essentially all the magnetic field is just shooting right past the area. And so the magnetic flux through this area is 0 when it's 90 degrees to the magnetic field. Okay. So a stationary charge emits an electric field.
Are those that order?
Because I think I stole a slide from someone and I didn't like the order it was in, and then realized that it was numbered, and so, but it makes more sense like this. So if you want to renumber it, you can renumber it. But there's just 4 big ideas. So a stationary charge, charges emit an electric field. They emit it radiating outwards. Other charges in that electric field feel an electric force. So an electric charge in an electric field feels an electric force. So one is just essentially saying stationary charges feel forces when they're in an electric field, and they also produce their own electric field. So the second bullet here, an electric current, essentially a moving electric charge, produces a magnetic field. So here we have to have a moving charge, an electric current. Now, if we have that moving charge, not only did it create a magnetic field, but if we take this moving charge and put it in another magnetic field, it feels a force. This last kind of sentence here isn't so important for the details of this class. The main thing is that moving charge in an external magnetic field feels a force. Then the last one is a changing magnetic flux produces an electric potential.